Assalamu alaikum. In the previous video, we have defined the multiple integrals. That is something like this. F of xy dx dy on a closed rectangular region. Okay, but if you want to calculate this integral based on the definition, you will find it virtually impossible. So how do we actually calculate this integral over a closed rectangular region? So that is the problem here. And the answer is the iterated integral that we will study here. First of all, suppose this region D is given as this Cartesian product of the closed intervals a, b, and c, d. Okay. So in the xy plane, this region should look like this. Something like this, and this is A, this is B, this is C, and this is D. And next, fix the value of x to some value, say x0. So we consider this function of y alone. By the way, we assume that this function f of x and y is continuous on this region D. Okay, so if we fix the value of x, then this is a continuous function of y. So according to the property of a Riemann integral of univariate functions, this is integrable. So from c to d. So we can calculate this integral. So this is just an ordinary univariate Riemann integral. So this integral has a parameter x0, and we replace this parameter with variable x so that we can define this new function f of x as this. So the variable y is integrated out already. So the only variable left is this x. So this is a function of x. Now, although we don't give a proof, we can show that this is a continuous function of x. Okay, so we can show that this is a continuous function of x. Function of x on this interval, of course. So since this is a continuous function, we can integrate it over this closed interval between a and b. So by substituting the definition of this uppercase f, then this becomes this. cd f of x and y dy dx. Okay, so we first integrated f of xy with respect to y, then we integrate that with respect to x. So this is called iterated integral. Iterated integral. And of course, we can do the similar procedure by swapping the roles of x and y. So we can first integrate with respect to x. Then we integrate the result with respect to y. Okay, and if this function f of x and y is continuous function on the region D, then we can show that these two iterated integrals are actually the same, and it is also equal to this double integral. In other words, we have the following equality. D f of x and y dx dy is equal to this iterated integral a, b, and c, d. And this is also equal to c, d, and a b x y dx and dy. So unlike the original definition of this double integral, the iterated integrals are easy to calculate. That is, we just iterate the integral of univariate functions twice. So that's how we can calculate the double integral. This is actually a theorem that we need to prove, but for the moment, I will skip the proof because we will prove this for a more general case in a later video. So just move on to an example. Okay, so let us find the integral, double integral of 2x plus y times x dx dy, where the rectangular region D is 0, 1 times 0, 1. So we apply the iterated integral. So this is equal to, first let's integrate with respect to y. 0y and distribute 2x squared xy dy first and then dx. So first calculate this part, and that is, let's see, so this is no y here, so 2x squared y plus 1 over 2xy squared, that is from 0 to 1. Okay, and that is, so y equal to 1, that is 2x squared, y equal to 1, that is 1 over 2x, and y equal to 0, that's 0 and 0, so that's all. Now we integrate with respect to x. That is, so this one, 2 over 3x cubed, and that is 1 over 4x squared, 0, 1. And that is 2 over 3 plus 1 over 4, that is, what is it, 12. 8 plus 3 is 11. So this is it. So in this calculation, we first integrated with respect to y, then integrate the result with respect to x. But we can do in the different order. That is, first integrate with respect to x, then integrate with respect to y. And you should check that. You should do that to see that it gives the same result. When the function f of x and y can be decomposed into the product of function of x alone and a function of y alone, then the iterated integral can be greatly simplified. That is, for example, if we integrate this cd and a b f of xy dx dy. So suppose f of xy can be expressed as this. So it's g of x is just a function of g alone, and h of y is a function of y alone. So in this case, cd and ab, g of x times h of y dx dy. Okay, now in this part, h of y is just a constant as far as the variable x is concerned. So this can be taken out of the integral here. Okay, so that will be this dx and h of y dy. But here, this part contains no y, so this whole thing can be taken out of the integral. That is ab g of x dx, and the remaining part is this c d h y dy. So this is just the product of two integrals. So we can completely separate the integrals. Let's see a simple example. Consider integrating a function exponential of x plus y, and the closed region here is between 0 and 1 times between 0 and 1. Okay, so this is, of course, so this exponential function, so we can split into the product. Okay, so let's call this d. Okay, and since this is a product of two functions, each of with no overlapping variables, so we can just split this into the product of two univariate functions, dx here times dy. So if we integrate this, this is, so it's just exponential function, so that's exponential and exponential. So this is just e minus 1, and the same here, so that's just squared, so that's the result. We can also apply the iterated integrals to triple integrals or general multiple integrals. For example, consider the triple integral the f of x, y, z, where, say, d is this rectangular region, a1, in this case, let's write a2 here, times b1, b2, times c1, c2. Okay, in this case, as long as this function, the integrand is continuous, then this can be calculated as this. Integral b1, b2, integral c1, c2, f of x, y, z. First integrate with respect to z, then integrate with respect to y, and then integrate with respect to x. Of course, you can swap the orders. Okay, you can first integrate with respect to x and so on. By the way, just to make this look a bit simpler, we may also write like this, a1, a2, dx. So we can, omit these parentheses, b1, b2, dy, and c1, c2, the function. Okay, don't confuse this with the product of this integral and this integral. Okay, it's not a product. It should be interpreted as this. Okay, we integrate this thing with respect to y, and we integrate this thing with respect to x. Okay, so this is just a shorthand for this, nothing more. Okay, let's see an example. Okay, so we want to integrate this function, sine x plus y times cosine z, dx, dy, dz, where d is this region. X is between 0 and pi half, and y is between 0 and pi half, and z is between 0 and pi over 6. Okay, so let's use the technique of iterated integral. But before that, we should notice that this part and this part can be separated. We can decompose into two parts. This cosine z doesn't include x or y, so we can separately integrate this part just with respect to z and forget about x and y. So in this case, so if we separate this z part, it will be between 0 and pi over 6 cosine z dz times the rest. Okay, and for x and y, we use the iterated integral pi half, let's say dy, and pi half d, let's see, sine x plus y dx. Okay. For this part, it's easy. That's just sine z. And for this part, we leave this part like this. And sine x plus y, if we integrate this with respect to x, then we have negative cosine x plus y, 0 and pi half, and dy here. So this is sine pi over 6 is, what is it? I think that's 1/2. And sine z is 0, so this part is just 1/2. So this part is just this. And this part, so when x is pi half, we have negative cosine pi half plus y minus, here's minus, so that's positive, and y. Okay, now cosine y plus pi half is actually it's sine y. So that is sine y cosine y dy. And well, if you want to prove this, just use that formula separating this trigonometric formula. So that's cosine a plus b is cos minus sine. So that's but cosine pi half is 0, so only sine part will remain, and sine pi half is 1, and sine y remains. So, and the negative sign is there, so the negative sign is swapped, and we have sine y here. So the result is that it's sine y, that's cosine y, plus this one sine y. And that should be, let's see, so that's 0, and that's 1. And that's, what is it, cosine 0, that's 1, and sine 0 is 0. So that's negative 1, so that's 2, so this is equal to 1. Okay, that's it. All right, that's all for this video. See you later.